In this video, we'll look at work and energy and focus on kinetic systems. Like most good things in life, what looks simple at first glance often has many layers of complexity if we look more closely. This is definitely the case with energy. Let's start with the fundamental law of energy conservation, which basically says that if we measure relative locations and states of motion in any system, we can perform a calculation to determine a quantity that we call energy. And if we perform the same measurement and calculation at any later time, this quantity remains constant as long as the system is left alone. Now, this is true for any system ever measured. As long as we look carefully, this quantity remains constant without exception. This is what makes a law in physics. The result is always the same. We don't know why, it's just the way that nature seems to work, without fail. We saw Richard Feynman when we looked at Newton's first law. He has an excellent analogy that he used in his introductory physics lectures. Here's how he introduces the concept of energy conservation.
I want you to imagine a child, perhaps Dennis the Menace, who has blocks, but you must appreciate that these blocks are absolutely indestructible and cannot be divided in pieces. Each is the same as the other, and we'll suppose that he has, say, 28 blocks. Now, this child is put into a room by his mother in the beginning of the day with his 28 blocks, and at the end of the day, I don't know why she's so curious, but she counts the blocks very carefully and discovers a phenomenal law that no matter what he does with the blocks, there are always 28 blocks. So this goes on for a number of days until one day there are 27 blocks, but a little looking around shows that there's some under the rug. You have to be careful to make sure that you look everywhere in order to make sure that the number of blocks doesn't change. One day, however, the number of blocks appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and now looking outside, you can find the other 2 blocks. So you bring them back in again, and everything's all right. Another day, careful count indicates the existence of 30 blocks. This causes a considerable consternation until it's realized that Bruce came to visit and he owns blocks, and left perhaps a few. So after we've gotten rid of some of these things, that we close the window, we don't let Bruce in, then we see everything's going along all right until one time when we count there are 25 blocks. But there's a box in the room, the toy box that the boy has, and the mother goes to open the toy box, but the boy says, "No, don't open my toy box," and screams. The mother is not allowed to open the toy box. Being, however, extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box, and it weighs 16 ounces, say. So the next time when she wants to check, she weighs the box again, subtract 16 ounces, and divide by 3. So she discovers the following: number of blocks that you can see, plus weight of box minus 16 ounces divided by 3 ounces, and then it's constant every time, up to a point. There then becomes some gradual deviations, but careful study indicates that that dirty water that's in the bathtub is changing its level. In other words, the child is throwing blocks into the water. You can't see it because it's so dirty, but you can find out how many blocks are in the water by adding another term to this formula, which is height of water in tub minus 6 inches divided by 1/4 of an inch, because each block that goes in is 1/4 of an inch. And so with a gradual increase in the complexity of the world, you find a whole series of terms representing ways of calculating how many blocks are in places where you're not allowed to look. And as a result of this, it's possible to find a complex formula, a quantity which has to be computed, which always stays the same in this situation.
One quantity that seems to obey this law is the product of force and displacement. In physics, we refer to this as work. We can see this conservation if we look at masses on a balance. We notice that placing the same mass equal distances from the fulcrum results in a stable condition. And if we remove one mass, the balance tips. Now, if we replace the missing mass closer to the fulcrum, it doesn't restore the bar to the balanced condition. Placing a second mass gets it closer, but it takes 3 masses to restore to the balanced condition. So let's look at this force displacement product. There are 3 masses on the left side of the balance and only 1 on the right. But if the distance between ticks on the bar is uniform, let's call this x, the 3 masses are at a distance of x from the fulcrum, while the single mass is 3 times the distance. So if we look at the height the masses on the left are lowered, the single mass is raised by 3 times this height, since these triangles are similar. Now the downward force on the 3 masses on the left is 3 times the weight of 1 mass, and it moves downward a distance of h. And for the mass on the right, it has a weight of just 1 mass, but moves upward a distance 3 times as high. This gives us products that are equal in magnitude, but with opposite directions, so this product for the whole system is constant. If we define work as the transfer of energy and use this product of force and displacement, we get this equation. We have a new unit for measuring this work, and that's the joule. We use an uppercase J to denote this unit, and 1 joule is equivalent to 1 Newton meter. Of course, we have to remember that force and displacement are both vectors, and we have to consider their directions in relation to each other. If we consider pulling a wagon like Richard Feynman described, we pull forward and upward while the wagon moves forward on the ground. So our force and displacement vectors are no longer collinear like we saw on the balance. Now we can use our understanding of component vectors to see what portion of our force, the x component, actually causes the wagon to be displaced in the x direction. So our work product here introduces this cos theta term, where theta is the relative angle between the force and displacement vectors. The mathematical term for this is the dot product of two vectors. Now we can do work on a system to increase or decrease its energy, and remember that this energy is calculated based on relative locations and states of motion. For now, let's look at energy associated with motion. We refer to this in physics as kinetic energy. In the friction video, we pushed a boulder with a bulldozer, but if we stop pushing, the boulder doesn't necessarily stop right away. It will continue forward until the friction slows it to a stop. So if the boulder was originally stationary and we got it moving by applying a force to travel a distance, we've done work, or transferred kinetic energy to the boulder. Note that the force and displacement are in the same direction, so we don't need the cos theta term. Now using Newton's second law, our force causes the boulder to accelerate while it's displaced. But remember in our big 5 equations, we could associate velocity's acceleration and displacement, so we can relate that acceleration-displacement product to a change in the squares of the boulder's velocities. But remember that our original velocity was 0, and if we just refer to our final velocity as v, we have this kinetic energy we'll denote with the letter k that's equal to 1/2 mv squared. Now a quick unit analysis shows that the resulting unit is still consistent with the joule we defined with work. And this leads to a kind of self-referencing relationship between energy and work. While work is the transfer of energy, energy is the capacity to do work. In logic systems, we refer to this as a strange loop. M.C. Escher, an artist of the 20th century, was famous for using these strange loops in his work. And this sort of symmetry is always associated with conservation laws in physical systems. This is known as Noether's theorem, named after a German mathematician, Emmy Noether, who developed the theorem in the early 20th century. So let's look at a sample calculation. Now suppose we push a 30-kilogram box along a horizontal surface a distance of 0.8 meters. If we push with a force of 120 newtons and there's friction of 5 newtons, we can determine the amount of energy transferred to the box from the work done to the box. So the net force will cause the box to accelerate, and the net force is the vector sum of our applied force and the friction, which are in opposite directions and have opposite signs. Using our work formula, we find that 92 joules of work was done on the box, giving the box 92 joules of kinetic energy. But what if we look at the work done individually by us and friction? Well, our force and the box's displacement are in the same direction, so theta equals 0 degrees, and the work we do is 96 joules. But the friction and the displacement are in opposite directions, and the relative angle between these vectors is 180 degrees, so the friction does negative work on the box. Still, if we add these two results, we get the same kinetic energy transferred to the box. So how fast is the box moving after traveling 0.8 meters? Well, for this, we can use our kinetic energy formula and isolate for v. When we substitute the known values, we find the box is moving at a speed of 2.53 meters per second. Now what if we want to determine how far the box will slide if we stop pushing? If we used kinematics, we could find the acceleration using Newton's second law and use one of our kinematics equations to solve for the displacement. But we can often simplify this by using an energy solution. Our net force here is only the friction, and the work done by friction will cause the box's energy to drop to 0 as it comes to rest. If we divide the change in energy by the F cos theta product, we get a displacement of 19.2 meters. Try using kinematics and see if you get the same result.